Welcome back, students. Today, I need to tell you a few things before we get into the lesson today. This would be the lesson for Friday, April 3rd. One thing I figured out as I was preparing this lesson is that apparently I miscounted when I was frantically running off all your papers and so forth that last day of school we had, which remember, we had very little notice that we weren't going to be returning to school the following Monday, which is actually today when I'm taping this. It's Monday the 20th, or Monday the 16th, sorry. And apparently I miscounted as to how many papers you would need to cover the entire 2 weeks we were going to be out, the weeks before and after spring break. And so this lesson is actually the first lesson in Unit 11-2. So I did not run off the notes packet for you for Unit 11-2, nor this first assignment. However, I will have them on Canvas. So I don't know if you'll all have access to a printer to be able to print those off yourselves. But if not, I'm not worried about that yet. I will get back with you again when we, the teachers, return to school on Monday, March 30th. At that time, I will send you an updated email, and perhaps I can maybe meet with you in some convenient place to get those papers to you. But in the meantime, I do want to go ahead and go over the lesson. The answer key to the notes is actually posted in Canvas, so you would be able to follow along there. Or if you have the ability to print off a copy of the notes from Canvas, then you would be able to do that too. So I apologize for that. And like I said, in the rush of trying to get all this stuff to you in time, I made an error. So again, I'm sorry. The other thing I wanted to mention today, so we do have a lesson we're going to go over and an assignment that would be due on Monday, April 6th, that I will be assigning a mastering from all the lessons leading up to today. All right. And so I will actually have assigned this, I believe, yesterday on this calendar here, which will be Thursday the 2nd. Normally I give you 3 to 4 days to do a mastering, and that's probably going to be the same this time. So the assignment, which is over units 10-2 and 11-1, would be due Monday the 6th at 7:30. Please note that it also includes a few problems regarding colligative properties, which were from unit 10-2, with boiling point and freezing point. The rest of them are acid-base related questions and problems. So again, I'm going to go ahead with the lesson, even though you don't have these papers in hand. Again, I apologize for that, but we will get that worked out when I return to school on Monday, March 30th. So let's get to today's lesson. So Unit 11-2 deals with redox reactions and electrochemistry. So we've dealt with redox reactions before. I commonly refer to the redox we've already done as baby redox. And now when we're getting into electrochemistry, into what we actually use redox for, I would commonly call this big boy and big girl redox. So we're going to get started on that today. So electrochemistry is the branch of chemistry that deals with the relationships between electricity and a chemical reaction. For a reaction of this type, a transfer of electrons from one atom to another must occur. In other words, it must be a redox reaction, and I'm pretty sure you have a good idea what those are. Remember, combustion reactions are always redox, as are single replacement. Combo and decomp can be redox depending on the reaction, and only double replacement reactions are never redox. So recall that an atom is oxidized if its oxidation number becomes more positive, meaning it has lost electrons. Recall also that the atom oxidized is also called the reducing agent because it forces another atom to be reduced. An atom is reduced if its oxidation number becomes more negative, and therefore it must gain electrons. And again, recall also that the atom reduced is also called the oxidizing agent because it forces another atom to be oxidized. So the substance oxidized is called the reducing agent. The substance reduced is called the oxidizing agent, because when either one of those things occur, the opposite must also occur as well. And so they are referred to as an agent for that opposite process to occur at the same time. So in the following net ionic equation here, which involves the reaction of zinc metal and hydrochloric acid. So this is a single replacement reaction. All right, the original reaction would have looked like this. Oops, zinc chloride, I should say. Zinc chloride solution and hydrogen gas. Remembering, of course, that these are AQ and these would be split or ionized. Our two chloride ions here would be spectators, and they would be removed. Leaving us with this net ionic equation. So again, this was a single replacement reaction. So the oxidation number of zinc increases from 0 to +2 here, as we can see. And the oxidation number of hydrogen decreases from +1 to 0 there. So zinc gets oxidized right there, oxidized, and hydrogen then gets reduced. Okay. In this particular reaction, the electron transfer also produces energy in the form of heat, as it is thermodynamically downhill and proceeds spontaneously. Delta G for this reaction is negative, so it occurs on its own without the addition of energy. So thermodynamically, this is a spontaneous reaction. In other redox reactions, the electron transfer can also be used to produce electrical energy. And in even other, this is on the next page, in even other redox reactions, electrical energy can be utilized to make an otherwise non-spontaneous reaction to occur spontaneously. So that electrical energy produced can be utilized to do that. Get that erased. Electrochemistry provides insight into such diverse topics as the construction of batteries. The battery industry is a multi-billion dollar industry worldwide, not just in this country, but worldwide. And if it wasn't for redox reactions, batteries would not exist at all. The spontaneity of reactions, electroplating, which is another very financially lucrative business in both jewelry and then also other industrial processes, and also the corrosion of metals. So electrochemistry is a very wide, diverse areas of very multiple uses in today's economy. Balancing a redox reaction. In order to balance a redox reaction, you must first remember the rules, assigning oxidation numbers for atoms in a compound. Remember those from Unit 6. Remember that all elements by themselves in their elemental form have an oxidation number of 0. Remember, metals hold true whatever their positive charge is as an ion, that is also their oxidation number. Remember, oxygen in nearly all compounds, except for peroxide compounds, has an oxidation number of -2. In peroxide, it is -1. Hydrogen, when bonded to a nonmetal, yes, is +1. And so when bonded to a metal, which is not all that often, it is -1. And all the rest of them, if you just remember those previous rules we just re-mentioned, you can figure them out with simple math. So here, there is also an additional requirement to balancing a redox reaction as compared to other chemical reactions. Now the gains and losses of electrons must also be balanced. So now we're going to take a look at the half reaction method. So although oxidation and reduction must take place simultaneously, remember you can't have one without the other, it is convenient when balancing them to consider them as separate processes. For example, in the following net ionic equation, again, the spectator ions have been removed. We're showing tin plus 2 in solution plus iron plus 3 in solution yields tin plus 4 in solution plus iron plus 2. So as you can see, tin is oxidized from plus 2 to plus 4. Iron is reduced from plus 3 to plus 2. The reaction appears to be balanced. You know, there's one tin here and one here, one iron here and one iron here, but the charges are not. If you just take a quick look, the total positive charge here is plus 2 and plus 3, which is plus 5. Over here, it is plus 6. So something's happened there with the electron transfer. It is not equal. So that means this reaction is not balanced electrically. So we're going to separate the two half reactions as follows in order to see how it must be balanced. So on the next page here, we have done just that. So we have taken the oxidation of tin and placed it as a separate reaction from the reduction of iron. And if we look at those then, for tin to have gone from a plus 2 charge to a plus 4 charge, it had to give up or release 2 electrons. And those electrons are written right there, okay? In the reduction of iron from plus 3 to plus 2, remember reduction is a gain of electrons while oxidation is a loss. Iron plus 3 had to gain 1 electron in order to be reduced down to a plus 2 charge. So I would have you note here that in the oxidation process, electrons are shown as products, while in the reduction process, they are shown as a reactant, okay? Just like when, you gain heat, it's endothermic, heat's on the left. If you lose heat, it's exothermic, heat's on the right. Well, you gain electrons, they go on the left. You lose electrons, they go on the right. Same principle, okay? Now it can be seen that the transfer of electrons is not balanced. Tin loses 2 electrons, but iron only gains 1. Remember, the transfer of electrons must be equal. So the coefficient 2 must be used in the reduction half reaction. And we will do that right there. And when you do that, and you add these two half reactions together to get back the whole reaction, with these electrons being on opposite sides of the yield arrow, just like we did in Hess's law, we can cancel them out, and here's what we're left with. Sn plus 2aq plus 2Fe plus 3aq yields Sn plus 4aq plus 2Fe plus 2aq. And if you look at that reaction, the ions themselves are still balanced, 1 tin, 1 tin, 2 iron, but not only that, now the charges are also balanced. Here we have a plus 2 and 2 plus 3s, which is plus 6. Add those together, you get plus 8. Here we have a plus 4 and 2 plus 2s, which is another plus 4, and you add those together and you get plus 8 as well. So plus 8, plus 8, the ions themselves are balanced. The whole thing is good now. So equations that show either reduction or oxidation alone, and we do that in order to balance them electrically as well as ionically or atom-wise, are called half reactions. Okay? So the last part to today's lesson is I'm going to show you how to balance a redox reaction if it is run in an acidic environment, in an acidic solution. Here are the steps for doing that. Number one, we're going to divide the equation into half reactions, one for oxidation and the other for reduction. It says note here, we're going to start each half reaction in the middle of the page. Sounds kind of weird, but you'll see here real soon why we're doing that. Secondly, we're going to balance each half reaction. Now, these are the steps that must be followed, and they have to be in this order, all right? First, we balance everything except H and O, everything other than H or O. Secondly, we balance the oxygen atoms on one side by adding water to the other, all right? We're in a solution, water is present. Third, we balance the hydrogen atoms by adding hydrogen ions to the appropriate side. Again, if we're in an acidic solution, not only do we have water in there because it's a solution in general, but since it's acidic, we have hydrogen ions as well. Lastly, balance the charge by adding electrons to the side with the greater overall positive charge. If one side is more positive than the other, we can bring that into balance by adding electrons to the side that is more positive. Those four steps must be done to each half reaction. Then, if necessary, multiply each half reaction by an integer so that the number of electrons lost in one half reaction equals the number of electrons gained in the other half reaction. They must balance. So this is if necessary. You might have to do that, you might not. Add the two half reactions and simplify where possible. That's just like Hess's law. And then check to make sure everything is in balance, including the charge. All right, so I've got one example to show you, and then we will call it a day. So we are going to balance the following reaction in acidic solution. All right, so first thing is we're going to break this reaction into half reaction. But notice it's already in net ionic equation form, so we won't have to deal with any spectators. Now, before we can split it into half reactions, we got to figure out what's being oxidized and what's being reduced. So for that, we're going to assign oxidation numbers. Well, a lot of them are already assigned for us. The chloride ion is, of course, -1. The chromium 3 ion is +3. It's already there for us. And hopefully you remember that Cl2, being a neutral element, its oxidation number is 0. So now we're going to look at the dichromate ion, Cr2O7 -2. Remember, oxygen in nearly everything, including this ion, is -2. There are 7 of them, all right? Now, there are 2 chromiums in here, keeping in mind that this is an ion and it has a charge of -2, all right? So 7 O's, 7 oxides is -14. The overall charge on the ion is -2, which means the total positive charge must be +12. +12 and -14 is -2. But there are 2 chromiums, and so we would take that +12 and divide it by 2, so that gives us an oxidation number of +6 for chromium. So based on that, what got reduced? Well, chromium got reduced from +6 to +3, and what got oxidized? Well, chlorine's -1 here, and it's 0 here. So that got oxidized. Now that we have determined that, we are going to split this reaction into half reactions. So we have a reduction half reaction and an oxidation half reaction. Now, I said earlier, we want to start in the middle. You're going to see why now. So what got reduced? Chromium. So the 2 substances that involve chromium will be in our reduction half reaction. and they are the dichromate ion on the left side and the chromium plus 3 ion on the right. Okay? Our oxidation half reaction involves chlorine. The two substances involved with chlorine are the chloride ion and Cl2 gas. So that would be Cl minus 1AQ yields Cl2 gas. So there are our two half reactions. Now we're going to balance them using the 4 steps we outlined on the previous page. We'll do that for each one. So the first thing is balance everything other than H or O. All right. So with this one here, anything other than H and O would be chromium. So here we have 2, here we have 1, 2 goes there. Chromiums are balanced. Secondly, balance O using water. Okay, well, there's 7 O's here. So we're going to balance that with water molecules. Well, how many O's are in a water molecule? 1. So how many of them are we going to need? 7. We're going to put those over here. So now that we have 7 O's on the left and 7 O's on the right. So that is done second. Third was to balance hydrogens on one side with hydrogen ions on the other, since we're in acidic solution. So here we have 7 times 2 is 14, which means we are going to put 14 hydrogen ions, and they're in solution, on the other side. So just to reiterate, we did everything other than H or O first, which was chromium. Needed 2. We balance O's on one side with water on the other. 7 there, 7 waters. Third, we balance hydrogens on one side with hydrogen ions on the other. 14 hydrogens there with 14 hydrogen ions there. Lastly, we balance the electron, or balance the charge using electrons. Whichever side is more positive, we will add electrons to that side to bring it into balance. So now we'll look at the charge. So over here, we have 14 pluses, which is plus 14, and this whole ion has a charge of minus 2. So plus 14 and minus 2 is plus 12. On the other side, we have 2 plus 3s, which is plus 6. Water is neutral. So over here we have plus 6. So the total positive charge on the left is plus 12. The total on the right is plus 6. We're going to add 6 electrons to the left side to bring that charge into balance. Because each electron has a charge of -1. So there's 6 negatives, and plus 12 is plus 6. Same as there. Balanced. That half reaction is done. Secondly, do the same thing with the others. This was going to be a whole lot quicker because in this particular case, first thing is we're going to balance everything other than H or O, which is Cl. That will take a 2. Second thing is balance O on one side with water on the other. There are no O's. We can skip that step. Third step is balance hydrogen on one side with hydrogen ions on the other. There are no hydrogens either. We can skip that step. Sometimes you can do that. The last step is balance the charge with electrons. So over here we have 2 times -1 is -2. Over here we have 0. We add electrons to the more positive side to bring it into balance. Well, 0 is more positive than -2, so we're going to add electrons over here. All right? And that would take 2 electrons to do that. So here we have 0 and 2 -1s is -2. Here we have -2, balanced. And before we finish, I want you to see one thing. I want you to be very clear about this. You should understand this. Reduction is a gain of electrons. In a reduction half reaction, the electrons should be on the left side of the half reaction. In an oxidation half reaction, electrons are lost. The electrons should appear on the right side of the half reaction. If that is not the case, you have made a mistake, right? You have made a mistake, and it should be apparent that something is wrong. So you need to make sure you understand that. Now we're going to add them together after we do one more thing. Remember, in a redox reaction, the transfer of electrons must be equal. Here we are gaining 6 electrons. Here we are only losing 2. We are going to multiply this half reaction by an integer. As it said, this may or may not be necessary. Here it was. By 3, which will then convert this to 6 electrons, which is the same as that one. That will also convert this to 3 Cl2s, and it will convert that to 6 chlorides. Now we're ready to bring it down. The electron transfers cancel. Nothing else here can be reduced or added. I would point out that if we had had hydrogen ions and waters in this half reaction here, that we might be reducing or combining them, as the case may be, just like we did in Hess's law with thermal chemistry. So always look out for that. In this particular one, we don't have to do that, but in many redox reactions, that will happen. So like I said, if there would have been waters and hydrogen ions in this second half reaction, we would be doing some reducing there, all right? But here we don't have to. So bottom line is we have 14 hydrogen ions. I just usually start with the top one and then do the bottom one. We have a dichromate ion. And then down here we have 6 chloride ions. That takes care of the left side. On the right side, we have 2 Cr plus 3 ions. We have 7 H2Os. And we have 3 Cl2 gas. And that is our balanced redox reaction. And I'm going to check it just to make sure. And you should always do this. 14 H's, 14 H's. 2 Cr's, 2 Cr's, 7 O's, 7 O's, 6 Cl's, 6 Cl's. And then check the charge. I have 14 pluses and a minus 2, which is plus 12, and 6 minuses, which is minus 6. So that gives us an overall charge here of plus 6. Over here we have 2 times plus 3, which is plus 6, 0, and 0. It's balanced. It's balanced by atoms and ions. It is also balanced by charge. So on your assignment, which again, I'm sorry you don't have it in hand yet, but we will figure out how I can get it to you if you need me to do that. You are just to complete that assignment, balancing redox reactions in acidic solution. So this was our assignment for our first assignment in Unit 11.2. I'm going to briefly go back to the, sorry about that, go back to the do nows. Maybe I can't do that. I can? Oh, there they are. There they are. There. So I want to briefly look at this one more time. So again, this would have been the lesson on Friday, the 3rd of April. So the assignment that you would have picked up today, that would be due on Monday the 6th. Also, please remember that I will have assigned a mastering assignment that covers a little bit from Unit 10.2 on freezing and boiling point with colligative properties, and then the rest of it involves acid base, the acid base things that we learned in Unit 11.1. Okay, not this. So anyway, that is the last lesson for now. This covers us all the way from the first week of school that we missed, which would have been March 16 through 20. Spring break would have been next, and then the following week, March 30 to April 3rd, this finishes up that week. So that is the 2 weeks that we talked about in class, the last day we were in session. Again, as I sent you an email outlining what your responsibilities were, as Dr. Hanback outlined in his letter to all of us, you are under no obligation to do any chemistry work that first week, March 16 through 20. That is essentially an extended or extra spring break week. But given the amount of material we have, if you have the time, if you're bored, or if you otherwise have the time to work on this stuff, that's why I wanted to make it available to you so that you wouldn't be crunched for time once the lesson or once we do return to school, whether it be here in class or via e-learning, as I believe we're going to start with e-learning April 1st through 3rd. So I hope that by providing this to you now, that you can kind of spread it out over a longer period of time if you so choose. Otherwise, enjoy your time off from school. I already miss you, and I'll look forward to seeing you hopefully on April 6th, which would be the Monday after this right here. So take care of yourselves, be safe, and I'll see you on Monday the 6th. Keep our fingers crossed that happens. Take care.